It is a privilege for me to deliver an introductory lecture on hadronic chemistry at this important international conference on hadronic chemistry held at the Department of Chemistry of RTM Nagpur University in India. It is a pleasure to thank the president of the university for the honors that we have received for the possibility of organizing this meeting at this important university. I would like also to thank all the administrators of the university. Needless to say, I want to thank the all faculty and all students of the university, as well as the organizer of this important meeting. My work is somewhat exemplified. Actually, this is supposed to be one of the easiest lectures of my scientific life. Why? Because there will be truly fantastic and extremely accurate and advanced talks on hadronic chemistry that the audience will have the opportunity to hear throughout this international meeting. So therefore, my role during this lecture is essentially restricted to a few historical recollection of the birth of hadronic chemistry, give us at least a feeling of the structure, the mathematics and the chemistry of the theory, and perhaps more importantly, dedicate most of my time to the proposal of new research, new application, and new advances of this new branch of chemistry, that are all intended to stimulate possible new technologies for industrial development, hopefully in India, since all those possibilities will be presented during this meeting in India for the first time. So therefore, the RTM Nagpur University, its faculty, and all interested colleagues should have priority of considering these possible developments over others. In my view, a theory can be claimed to be exactly valid under certain conditions when, for said conditions, the theory represents the totality of the experimental data from first principles without adulteration, namely without throwing free parameters, throwing free functions, and so on, that are then fit from the data. It is my view that quantum mechanics is indeed exactly valid, I repeat, exactly valid, for the structure of one hydrogen atom. Why? Because the theory was able to represent the totality of all rather complex experimental data on the structure of the hydrogen atom directly from first axiomatic principle without adulteration. We should also take the opportunity to express our appreciation and praise to the colossal minds of the originator of this scientific event, such as Schrödinger, Heisenberg, Bohr, and the others. Why? Because they were able to achieve a representation of the complex, very complex structure of the hydrogen atom without ever seeing it. So it was one of the most beautiful constructions of the human mind in history, in my view. Very well. So now let's consider two hydrogen atoms put together in the hydrogen molecule. Question: is quantum mechanics, and therefore quantum chemistry, exactly valid for the hydrogen molecule? This is a fundamental question for this conference. My personal view is that the answer is no. And the reason is that quantum mechanics and quantum chemistry have been unable, in 1 century of efforts and the river of public money, they've been unable to achieve an exact numerical representation of the binding energy of the hydrogen molecule from first unadulterated principle. In fact, there is the historical 2% of the energy which is missing. 2% is not that small, because it corresponds to 951 kilocalories per mole. So therefore, the fundamental question that I considered almost half a century ago during my graduate studies for the PhD at University of Torino, Italy, in the mid-60s, the fundamental question is, okay, so certainly quantum chemistry is valid as a first approximation, of course, this is out of question. But the important scientific issue is, what is the covering theory, the broadening of quantum mechanics and chemistry that will allow to achieve in due time, we are talking about the mid-60s, will allow us to achieve in due time an exact, numerical exact representation of the binding energy of the hydrogen molecule. I should add that I had problems with my chemistry teachers during my PhD studies in the 60s in Torino, at the University of Torino. Why? Because I consider the notion of valence to be a pure nomenclature. In the following sense, of course, the notion of valence has its scientific value. This is obvious. I should not even mention at this learned gathering of scholars. Also, we should praise the incredible discovery, advances, development done by chemists in the past century by using the notion of valence. But again, the issue, can we stop at that point? No. Human knowledge must advance. A scientific treatment of the valence, in my view 50 years ago, and is still my view today, requires first a mathematical treatment that produces an equation. Unless we have an equation, we do not have a quantitative treatment, and therefore we do not have the scientific treatment as universally defined in academia. Secondly, this equation has to produce a force, and the force has to be, of course, attractive. So because the hydrogen atom, they attract each other. They are not separated, they attract each other. Third, to be scientific, this attractive force must represent the totality of the experimental data in the hydrogen molecule. This scientific scenario did not exist in the 1960s, so therefore I decided to undertake a rather long scientific journey that brought us today at this beautiful campus in beautiful and historic India. I should recall that all serious chemists knew about this insufficiency, this historic missing of 2% of the binding energy of the hydrogen molecule. So therefore they proposed the so-called screening of the Coulomb law, which is depicted in this equation. Namely, is given by the multiplication of an arbitrary function of unknown physical or chemical origin, which multiplies the Coulomb law, and this function is then fitted from experimental data. Of course, the screening of the Coulomb law did allow the achievement of the missing 2%. However, and of course, as such, it has scientific value. But again, those are obvious aspects. We should not even mention in this gathering of learned scholars. The issue is another. Is this the final version for the representation of the binding energy? Ladies and gentlemen, no. In my view, with full due respect to past work, we have to go forward and develop new vistas, new ideas. Why so? Well, for many reasons, but above all, because the quantum of energy exists for the Coulomb law, for the Coulomb potential. Once you multiply the Coulomb potential for an arbitrary function, then you will end up with what's called a screened Coulomb potential, for which the quantum of energy has no physical or chemical meaning at all, has lost the physics, because there are no longer quantized orbits for the screening. Therefore, I question calling quantum chemistry the research via the use of the screened Coulomb potential, because the quantum is missing. There are additional problems, such as this implies a violation of the Galilei symmetry. Consequently, there is the violation of the imprivativity theorem, as a result of which even the quantization via screened Coulomb potential is in question. But back in the 60s, I found additional problems with quantum chemistry for a correct and accurate representation of molecular structure. This point was subsequently proved in a rigorous way by one of my graduate students while I was at Harvard University. The point in 1960 was the following. Since the notion of valence is so loose and the electrons are not tightly bound together, then their orbitals are free, essentially free, to orient themselves in space. And therefore, the prediction in the 60s that was verified in the 80s while I was at Harvard by the graduate students was that the contemporary quantum chemical notion of valence implies that the orbitals of any matter, any substance, can be oriented under a sufficiently intense external magnetic field. Therefore, the prediction of quantum chemistry is that all substances are paramagnetic. I could not accept this prediction. That usually is not indicated in the graduate school at Harvard, MIT, Berkeley, London, Paris, and Moscow, and other universities around the world. So I confronted this situation, at least try to identify the problem as accurately as possible, which is a necessary premise for its solution. The second central issue of my PhD studies in the mid-60s at the University of Torino was the following. Hydrogen atom is totally neutral, has no polarization, nothing, and is perfectly spherical at ambient temperature. So therefore, when we put together two hydrogen atoms, according to quantum mechanics and therefore according to quantum chemistry, there cannot be no force whatsoever, let alone an attractive force that binds those two to such a degree to have a very high binding energy. Now, this is a fundamental point that I encourage all colleagues of any, with a young mind of any age, whether you are a teenager or a senior scholar, is a point to ponder. Since the quantum mechanics and quantum chemistry, they admit no force whatsoever, they can explain how to bind those two together. What does this mean? My personal interpretation, but I invite my personal interpretation, I invite other interpretation, is that nature indicates sufficient evidence to expect that in the binding of two hydrogen atoms together, there is the birth of a new interaction, which is structurally beyond quantum mechanics and quantum chemistry. I pondered on this point for decades, and I found no other alternative. Now, the statement beyond quantum mechanics and or outside quantum mechanics and quantum chemistry technically implies that, and you'll hear on this point beautiful lecture during this conference, implies that that the representation of the binding force of two hydrogen atoms must necessarily require a non-unitary theory. The non-unitary character of the covering theory is mandatory because it's necessary to exit from the class of equivalence of quantum mechanics and chemistry as a condition to admit new forces, new attractive force. So my journey initiated at the ultimate, most elementary level of molecular structures, namely the coupling of two valence electrons that, according to the Pauli principle, must necessarily be in singlet coupling, namely with opposite spin. Now, the difficulties that I had with my teacher of chemistry during my PhD study was the following: that according to quantum mechanics, two identical electrons must repel each other. According to quantum mechanics, two identical electrons must repel each other. And positively should not attract each other. So therefore, in the electron valence coupling in singlet, there must be a new force. In other words, the new force, the new theories, everything that virtually the entirety of this conference will be devoted on this issue at the very, very ultimate essence of the structure of molecular phenomenology. Namely that, sure, the electrons, they have a point charge, but there exists no point-like wave packets in nature. I repeat, this is not stated very often. there exists no point-like wave packets in nature. What does this mean? It means that since the wave packets are extended, when particles such as electrons couple each other at a distance of the order 1 Fermi, then you have this situation here of a wave overlapping. Namely, you have a volume of wave overlapping, and this is the origin of the new interaction as well as the origin of hadronic chemistry. It was very easy 50 years ago. It's been confirmed throughout all those years that this interaction is fundamentally new. And it's called today non-non-non, in the sense that it is non-linear in the wave function. It is non-local in the sense that it occurs over a volume that cannot be reduced to isolated point. And third, it is non-potential, namely it cannot be described with a Hamiltonian because it is a contact type. This non-non-non character confirms that indeed this interaction is outside quantum mechanics and chemistry. Those ideas were clear. And they remain essentially unchanged. Now, why? It took 50 years finally to reach this beautiful meeting here in India. Well, there is a reason. That in my view, and this particularly a message for young researcher, namely that in my view, whenever you have a new problem, you have to look for the correct mathematics for its treatment. If you try a new problem, either with the old mathematics or with a mathematics that is not appropriate, you waste your time. You will die an unknown. So the issue 50 years ago was what type of mathematics is out there in the scientific community that allows me an invariant, in the sense that numerical predictions are invariant over time, an invariant representation of those interactions of non-linear, non-local, and non-potential. It was easy to see that they did not exist 50 years ago, and they had to be constructed. Therefore, as a physicist, I had to spend virtually the 80% of my time over 50 years to develop the mathematics that is needed for the invariant representation of this new interaction, since the mathematics did not exist. And that is the reason why it requires such a long journey. Now, at that moment also there was some controversy. We're talking about again 50 years ago. Namely, I was interested more generally, not only to the valence coupling, but I was interested to the general problem at large, which is known as the interior dynamical problem, which can be defined as the dynamics of extended bodies, such as macroscopic bodies or wave packet, moving within a physical medium, or electromagnetic waves moving within a physical medium with consequential non-non-non interaction. My teacher used to tell me, Ruggero, you are interested in a problem that does not exist. Their viewpoint was, no, look at the space shift during re-entry in our atmosphere. My teacher used to tell me, Ruggero, there is no need to study the problem because you reduce the satellite to its elementary constituents, you recover quantum mechanics at the level of the elementary particle, and there is nothing new. I disagreed. Then I disagree now. And for this reason, during my graduate studies, I formulated and improved a number of so-called no-reduction theorems that still remain known to a certain extent in the scientific community, to the peril of the scholar who does not take them in due consideration. So the theorems are elementary. It can be proved by a first-year graduate student. You will hear them a number of times during this conference, but very briefly, the theorem says that a macroscopic, non-conservative and or irreversible system such as this one cannot be consistently decomposed into a finite number of elementary particles, all in conservative and irreversible condition. This is just a dream. And vice versa, if you have such a collection of particles, you will never represent nature as it appears to us. What does it mean? This means that irreversibility originates at the most elementary level of nature. And here I have to praise Professor Balekar, Anil Balekar, because he understood this point in all its depth. And this is a point that has brought us to our collaboration and eventually developed into this international conference. Because the reversibility that Professor Balikar and others that are studying at RTM Nagpur University now originates at the most elementary level of nature. This means that we have to look for a mechanics that is compatible with thermodynamical laws. The entire view and perspective and value and relevance of thermodynamics is dramatically improved and enlarged systematically. Once the field of research was identified, again we are talking about in the 60s, then namely interior dynamical problem, then the next step was obvious. Look at the original Lagrange and Hamilton's equation, not the equations that you can read in 20th century literature, because they have been truncated to adapt the historical analytic equation to Einstein theories and quantum mechanics. What are the original equations? The original equations, this is Lagrange equation, they have external terms. I studied in Torino, where Lagrange wrote most of his work in Italian. I read them. Lagrange was very clear. Nature admits forces that we can represent with a function that today we call the Lagrangian. But there are other forces that cannot be represented, and he puts them in the external term. Hamilton did exactly the same thing, independently from Lagrange. Jacobi did the same. So I said to myself, okay, so I now go back to the historical true, they're called now the true analytic equation, those with external terms, and then I can describe everything. Start from there and then go quantization, or if you want, operator mapping, and do everything. No, it was soon, we're talking about back in the 60s, soon it was clear that this avenue of research was not recommendable. Why so? Well, because when you look at the bracket of the time evolution, then you not only you see a conventional Poisson bracket, namely verifying the Lie algebra, but you see an additional terms induced by the external term in the analytic equation. And unfortunately, those external terms violate some of the axiom for this bracket, this entire bracket, to characterize an algebra. So when you have external term, not only you lose all the algebra, forget about it, they are gone. When you start irreversible system, don't think about the algebra, you will be wasting your time and die in unknown. Now, you need fundamentally new theory. But the point is that you lose all algebra, and so I was not in a position to build a covering theory. I am a strong believer that science advances by step. Every step has to be a covering of the preceding step. Einstein is Einstein not because he said Galileo is wrong. No. Einstein is Einstein because he said Galileo is correct for low speed, and for high speed, my special relativity is better. And he added, not only but special relativity is a covering of Galilean relativity, because when the speed becomes small, then the Galilean relativity is recovered identically. This is a beautiful teaching in the history of science. I could not jump and waste my time in disconnecting myself from special relativity, disconnecting myself from quantum mechanics. No. So the issue was to locate for a covering algebra that allows us to represent irreversibility and interior dynamical problem at large as well, but here is the key point. However, admitting in its classification or under a clear limit, admitting Lie algebra, because Lie algebra are the foundation of all main theories of the 20th century. So the next problem was the following. We are still talking about the 60s. All theories of the 20th century, the major ones, are reversible over time. For several reasons. For instance, Einstein's special relativity is reversible over time. Why? Because the Minkowski line element is quadratic on time. Since it is quadratic on time, where you go forward or backward in time makes no difference. So therefore, special relativity admits with equal probability motion forward in time and backward in time. Well, it's exactly the same thing for quantum mechanics. Only we are talking about a statistical probability is identical for motion event forward in time or backward in time. Why? It's mandatory, it's a mandatory consequence. It's not stated in the best PhD courses at Harvard, MIT, Berkeley, Paris, London, Moscow, and other, or Beijing, because of political reason. But the ultimate reason is that of the reversibility is that the Lie bracket, namely AB minus BA, verifies this symmetry, is invariant under anti-hermiticity. I repeat, the ultimate root of the reversibility of 20th century theory is the basic theory, Lie algebra, are invariant under anti-hermiticity. Anti-hermiticity is precisely one of the operations in which we go backward in time. Since there is an invariance under that operation, the theory has admits both forward and backward motion. So I pose myself for my PhD thesis the problem. I have to look for an algebra, so I have to verify all axioms of an algebra, but an algebra that breaks this symmetry, so that it is neither totally symmetric, not totally antisymmetric. In this way, we reach my PhD thesis of 1967 and a couple of papers immediately thereafter, in which essentially I proposed a broadening of Heisenberg equation in their infinitesimal form or in their finite form, in which the algebra, as you can see, is modified. I called it a mutation at that time. Later on, it was called the deformation. Namely, I multiplied AB and BI by P and Q scalars. They were non-null numbers. This algebra turned out to be Lie admissible because the antisymmetric bracket is Lie. You will hear this several times during the important point, however, is that this is irreversible over time, because if you do the time conjugation, you have a completely different event. So it verifies causality. Those equations of 1967 are the birth of hadronic mechanics and therefore of chemistry. They were not called hadronic mechanics at that time. The next step occurred at Harvard University in 1978, and while I was under support from the US Department of Energy. During that time, in these papers here, I proposed the following generalization of the preceding PQ equation, but is also the most general broadening of Heisenberg equation of Lie admissible type I could conceive it at that time by sandwiching operator R and S rather than parameter Q and Q between the product, the associative product of operator A and H. This is the infinitesimal form that I proposed in 78, and this is the finite form. The exponentiation of this expression into the other one is elementary. I recognize that this is an equation that will resist the test of time. And I have requested that when I die, I would like to have this equation engraved in my tombstone, because it will take some time to generalize this equation, not only in this form that I proposed in 78, but also in the hyperstructural form that you will hear very soon during this conference. In view of this rather broad character for the representation of irreversible system, then I proposed the name of hadronic mechanics during those papers of 1978. Even though hadronic chemistry was not mentioned in this paper of 78, lifting quantum chemistry into hadronic chemistry by the use of those equations is implicit. And so therefore, I assume that those equations, those papers are also the birth of hadronic chemistry as we understand it today. Now, immediately after the formulation of those, the fundamental equation of hadronic mechanics and therefore of chemistry for irreversible processes, I immediately realized a number of aspects. First of all, there was a particular case in which the R and S operator are the same, and the bracket verified the Lie algebra, but they are dramatically broader, structurally broader than the Lie algebra, and they are important for a number of applications, namely for systems that are closed, namely that they are isolated from the rest of the universe and therefore verify total conventional conservation rule. Yet the internal dynamics is more significant for thermodynamical studies. There are internal evolution, maybe the entropy, etc. So this was the Lie isotopic subclass of the Lie admissible algebra. Secondly, I realized that elaboration of the Lie admissible as well as Lie isotopic equation via the mathematics of quantum mechanics was catastrophically inconsistent. I repeat, despite the broadest possible, any application of those equations via the use of the mathematics of quantum mechanics, namely Hilbert spaces, conventional numbers, real conventional functional analysis, and so on, is catastrophically inconsistent because it does not preserve hermeticity in time, it does not preserve the unit of measurements, it does not preserve under time to numerical prediction, etc., etc. To become a serious scholar in this new theory, in this new covering theory, it is essential, in my view, that the interested colleague study those are called theorem of catastrophic mathematical and physical inconsistency of non-unitary theory when formulated with the mathematics of unitary theories. They are crucial to avoid the major pitfall of wasting years of research. This took about 30 years. Maturity was only achieved in 1995 with the publication at a special issue of the Rendiconti Circolo Matematico Palermo, and this mathematics, now called genomathematics, was studied in details at recent meetings in Greece. It will be studied. It will be presented by outstanding lecture by colleagues during this meeting. So therefore, I apologize. I cannot review it. Otherwise, it will take me a couple of semesters to complete my lecture. From this moment on, I have to assume that you know this new mathematics is called genomathematics for the invariant treatment of of irreversible processes, and with a particular case, the isotopic mathematics. Now, you will hear very often the following statement, sometimes expressed in good faith, sometimes not. Namely that, oh, Santilli, new mathematics is too complicated. Oh, no, I am an experimentalist. No, it's too complicated. It's too fancy. Well, be careful, because unless those type of statements are expressed in good faith, in which case should be respected, unless they are expressed in good faith, and they are insidious. Namely, they are intended to manipulate politically the opinion of the interlocutor and so on. The reason is the following, that besides this new mathematics, we have now our theory, after so many years, decades of work, we have reached such a maturity that we have developed very simple means for the construction of those covering theory, starting from a given quantum mechanical or quantum chemical model. It could not be simpler than that at the level of first-year graduate student. What do we do? Well, we represent the non-non-non interaction with a generalized unit. Then we assume a non-unitary transform to be equal to this generalized unit, and then the method is elementary. You subject the totality, I repeat, the totality of operators and quantities and their various operations, you subject everything to such a non-unitary transform, beginning from the unit, then the product, Schrödinger equation, etc., etc. And with a simple non-unitary map, you build everything that you need. Look at here. This is the fundamental equation of hadronic chemistry for the hydrogen and water and other molecule. And this non-non-non interaction are embedded in this operator T, which is the inverse of this generalized unit. It comes very naturally from this non-unitary map. Then it's very also elementary to prove that this is invariant under additional non-unitary transform. However, careful, don't make a minestrone of different mathematics. You are now working on isochemistry. This requires isomathematics. The totality of the mathematics has to be isotopic. This means that you cannot study the invariance of this Schrödinger equation by using a conventional non-unitary theory. That's a minestrone. It's like studying the invariance of the conventional Schrödinger equation by using isomathematics. It's exactly the same. No. Therefore, you have to reformulate the non-unitary transform in terms of of the new isomathematics. This is essentially the isounitary transform. Then it's very easy to prove that indeed you have invariance over time, you preserve hermeticity, etc., etc. A little observation here. Notice that this is isolinear. So therefore it allows to verify the superposition principle. This seems to be an insignificant point. It's an enormous... See, one of the technical difficulties that we had in studying the hydrogen molecule or the water molecule, those are bound systems of more than one particle. So for me to give, for anybody to do a quantitative treatment, we have to verify the superposition principle. If I embed the non-linear term in the Hamiltonian and use quantum mechanics, I cannot do it. I cannot study a complex structure with more than one constituents with a non-linear quantum theory. It is inconsistent. You cannot decompose it into factorize the various states. And there are many, many difficulties. Now, this is instead isolinear. So this does allow me, in fact, to represent a complex structure, a bound state of more than one particle, via nonlinear theory which is nonlinear in the wave function. Then the genomathematics is the same, but in this case you have to embed the direction of time in the most ultimate possible mathematical entity, which is the product. The problem was how to represent irreversibility. Well, in an invariant way, namely in a way which is invariant over time, preserving observability, etc., etc. After looking at all spending a decade in all possible alternatives, the only solution that I found, first in 1993 as far as the number is concerned, and then in 1995 regarding the entire genomathematics is concerned, was to embed irreversibility in the most elementary and fundamental mathematical operation, which is the product. So therefore, I assume a product which is ordered to the right for the representation of motion forward in time. Order to the right means that 2 must multiply by 3 to the right. And then I assume the product order to the left, namely 3 multiplied by 2 to the left, I assume as representing motion backward in time. Then the differentiation of those two products via different isotopic element guaranteed that the time reversal invariance of the genochemistry is indeed is physically inconsistent, is outside the theory, and therefore the principle of causality is preserved. In this case, however, this is technically realized in a very simple way by using two, not one. One non-unitary transform is good for the isochemistry. For the genochemistry, to introduce an ordering, you need 2. And in this case, for instance, U and W. U and W dagger for motion forward, or W U dagger for the motion backward. Restricting to only the motion forward, what you end up with an ordered product which has this structure and this, and therefore it is also invariant. The next level of hadronic chemistry is known under the name of hyperchemistry. At this point, we have to be honest with each other, and the theory becomes rather complex. And the reason is that hyperchemistry is based on hypermathematics, in particular on the hyperstructure in the form formulated by Vojuklis and other mathematicians. We are talking about the most general mathematics that can be conceived by the human mind. Therefore, we have to be reasonable, and we have to expect some complexity both in the conception as well as in the formulation of the mathematics and its implementation into hyperchemistry. However, the elementary notion can be understood by everybody. The idea which I formulated in 1992 at this monograph, which was published by the Ukraine Academy of Science, is the following. Consider 2 atoms of a given DNA molecule. Then the biological interaction or correlation of those 2 atoms of the DNA eventually will produce an entire organ, such as an eye, with 10 to the 30, 10 to the 40 atoms. But the biological correlation of 2 atoms in a DNA can be mathematically represented with a product. So the very, very principle, the very, very structure of the DNA, in my view, in 1992 and still is today, is that it is an hyperstructure, namely starting from you have an operation, the multiplication of two quantities, and you produce a set with a very large number of elements. Very well. So therefore, in 1992, I recommended to realize the generalized unit, now called the hyperunit of hyperchemistry, as an ordered set with a very large number of elements. In this case, let's say 10 to the 30. And this is multi-valued, but exists in our three-dimensional space, so as a necessary condition to achieve compatibility with our Eustachian lobes. So those theory is three-dimensional, but multi-valued. They have many, many, many values. Once you generalize the unit in this fashion, then the inverse will characterize a product. In this case, 2 multiplied by 2 to the right, forward in time, again irreversibility. The DNA and the creation of an organism from the DNA is a clearly irreversible process. So we insert order in the very fundamental multiplication. But in this case, 2 multiplied by 3 may give rise to 10 to the 30 results with evident mathematical complexities. This is the very birth of the attraction among 2 identical hydrogen atoms. I don't have the time to review. They will have a magnificent lecture to be delivered during this workshop. Let me briefly flash to you some of the successes of hadronic chemistry, but only for its isochemical part, because we have not yet application for the genochemistry, let alone hyperchemistry. You will hear magnificent lecture during this international gathering here in RTM Nagpur University, so I will be very, very quick. So the first one I want to bring to your attention is the achievement indeed of the exact numerical representation of the binding energy and other characteristics of the hydrogen atom that I achieved in 1998 with my American colleagues, a chemist, Don Schillerdi. Then another success I would like to mention is the achievement of the exact numerical representation of the binding the characteristics of the water molecule. Another one which I would like to mention is the achievement of a new chemical species that I will call magnecule, because their primary bond is of magnetic time, even though there are several other contributions. I can only mention that for me to predict in this new species and verify it experimentally, since the original memoir of 1998, I had to achieve first a deeper understanding of the conventional molecular structure before I could differentiate it into a new chemical species. And that's the reason why this formulator was only in 1998. Then those are the original slides of 1998. Here is the spectrum of this gas. It's called today Magna gas, and it is produced by the company that I formed under the name of Magna Gas Corporation. The company became public in 2007, and I pushed the company all the way to be traded at NASDAQ under the symbol MNGA. Mary Nancy George atom. Here you can see in 1998 the structure is from 40 to 400 atomic mass unit. You see all lots of peaks, very fully identified by the GCMS. But however, they are not identified as an ordinary molecule, but that was not sufficient. The equipment was also had an infrared detector, so the same spectrum was investigated under the infrared, and as you can see, it's flat. So you should have seen here all sorts of signature of those peaks. This is clear evidence that virtually most of those peaks cannot be ordinary molecule. because then there will be resonance. Recently, Magna Gas Corporation has managed to, following my pushing and funding, I push for funding and so on, we now have a very nice analytic laboratory in Tarpon Springs, Florida, with all sorts of various equipment specialized for the detection of magnecule. This is, for instance, a GCMS equipped with infrared detector. We also have gas chromatographic thermal conductivity detector, very specialized scales, and so on. These are some of the scans that we obtain in our laboratory under the direction of Dr. Young, and here you can see again. You can see peaks in the GCMS, and then you go infrared, and you see no signature at all, confirming the 1998 paper and confirming several other papers. There is one comment I have to make in regards to the magnecule. You will hear repeatedly, at least I heard repeatedly, by a number of colleagues, including Nobel Prizes in chemistry, who call me, former colleagues at MIT or Harvard, say, Ruggero, why you claim that this gas that you produce and called Magna gas contains this new chemical species of magnecule? They don't exist, because look at the scan. Here I send you by email the scan of with our best gas chromatographic equipment available at MIT shows no anomaly whatsoever with respect to molecule. Ladies and gentlemen, be careful about this type of statements. They are, in this case, were done in good faith. They have to retract. So in a way, they lost this famous colleague. They lost, in part, their faith. To understand the embarrassment of distinguished colleagues, I have to clarify the following point. Let's go back in time when the chemistry community created and then established a variety of equipment for the detection of molecules. I'm talking about gas chromatography, mass spectrometry, infrared detector, etc. Now, what was the fundamental requirement that at the basis of such a very successful series of equipment that works so beautifully for molecule? The fundamental requirement was the following: that the energy of the detection mean must be significantly smaller than the binding energy of the molecule that you want to detect. In other words, suppose you want to detect a CO molecule in a GCMS using ionization technique. In this case, the energy of the ionization process must be significantly smaller of the binding energy of the CO. Because if you use very powerful ionization process with an energy bigger than the CO, you can smash the CO and detect nothing. Exactly the same applies for the infrared detector. They use laser. The energy of the laser in the infrared detector must be smaller than the binding energy of the molecule you want to detect. Otherwise, you don't do nothing of science. You just do mambo jumbo. Exactly the same is for the thermal processes of the GC-TCD, etc., etc. Very well. This is very well known, but here is the point that distinguished colleague had to retreat their statement. And now, to do science for the detection of magnecule, we have to apply exactly the same rule, namely the energy of the ionization means for the GCMS, the energy of the laser, of the infrared detector, the temperature of the operating means for the GC-TCD, etc. Those energy have to be lower. And here is the key point. This time have to be lower of the binding energy of the magnecule. Otherwise you smash them and you claim to have it. Now, and here is another point. But magnecule were conceived to have a binding energy much smaller than molecule, as a necessary condition to improve combustion and therefore decrease contaminants in the exhaust. But not only it is necessary that the detection mean must have an energy below the binding energy of the molecule, not of the molecule, because you want to detect molecule, not molecule. That's not enough. All magnetic bonds, they have a Curie temperature at which they disappear. So in addition to the energy has to be lower, the temperature at which you use the equipment has to be below the Curie temperature of the molecule you want to detect. So if you use those rules, I can assure you, now has been tested and verified and re-verified many times, I can state with confidence, then and only then you will detect molecule and you will do science. Otherwise, I don't know how to call it. This is something that we detect very often in our laboratory in Florida. Look at this. This is a peak 19 atomic mass unit. Namely, this is H3O. I repeat, this is H3O. This is COH 45, etc. I have not published a paper on this. If any colleague is interested in joining me, I'd love to write it together, to complete it together. We have 3 different means of detecting this anomalous species. This slide is to give you an idea, a feeling of the complexity of magna gas, namely the gas that has a molecular structure. You see here all atomic mass units from 2 all the way to 400 in measurable amount. They are small, but sometimes some are big, but they are measurable. And they are over the background, so they exist. It is obvious that all this cannot possibly be molecule. It's very easy to prove. Some of them, they may, of course, but not all of them. Very well, this is an idea how that we represent conceptually the molecule. Careful, that is a conceptual rendering, just to help our mind to understand. But the reality is dramatically more complex than what you see here. Here in this molecule, not only you see, of course, the magnetic attraction between the 2 toroids, but then you see the polarization of the electron spin and the nuclear spin and the contribution of Coulomb type and many different. But it has been proven that the overall sum of all those contributions is attraction. It's rather strong attraction, 1,315 times stronger than the nuclear magnetic moment. Another success of hadronic chemistry is the prediction of a new species of hydrogen I made in 2003 that can be as pure as hydrogen as you desire. In this test was 99.8. Yet the specific weight is a multiple the specific weight of conventional hydrogen. In this original derivation that was published in Oxford, the International Journal of Hydrogen Energy, this new species of hydrogen, now called magna hydrogen, was 7 times had 7 times the specific weight of conventional hydrogen. Magna Gas Corporation is now organizing the industrial production of this new species. Here is a vacuum swing adsorption separation method from magna gas that we have in Florida. The last application of hadronic chemistry that I would like to bring to your attention, which I personally believe is perhaps the most interesting, is that the molecules are, in my knowledge, limited knowledge and understanding, are fundamental for the new nuclear fusion without radiation that now are established apparently beyond any reasonable doubt, because they've been systematically proved with a variety of reactors. We have 7 reactors here. We show the first one, very simple. Here we show the one of the latest that we even produce steam. I would like to close this lecture with a recommendation of a few research projects that I consider to have some significance, in particular because they may lead to new technologies, and therefore to new industry, and therefore to new application. This is, after all, the main scope of my research, the main scope of hadronic chemistry, and therefore the main scope of this important gathering. The first research that I can possibly recommend is to develop genochemistry for a quantitative representation of chemical reaction. Chemical reaction, such as the burning of coal, is irreversible over time, and therefore should be treated, in our view, according to by genochemistry. There was a statement in the internet, I think in September, just prior to the meeting in Greece, essentially saying that mankind has discovered fire about 4,000 or 5,000, 6,000 years ago. But only recently, and apparently only at this last meeting in Greece, mankind has initiated quantitative studies for the representation of fire in a consistent way. Why so? Because quantum chemistry is reversible over time, so you need genochemistry for a consistent representation of such an irreversibility. I don't have to state to this learned audience that the moment we understand deeper this process and we know how to represent quantitatively, then possibilities are endless. You can go to an electric power company and we can improve the combustion and decrease the pollutant in the exhaust. Next, I would like to recommend quantitative studies on the anomalous flame temperature of magna gas, which has been certified by the City College of New York as being over 10,000 degrees Fahrenheit. This means that the magna gas has a flame temperature more than double any commercially available fuel, gaseous fuel. You have to see the magna gas cutting a 12-inch thick steel slab like butter. So, and this is an idea of the flame. Also, there are indications that in the flame of magna gas there are spectral lines that are the same as in the sun, and they are not yet been interpreted because they are not predicted by quantum mechanics. They are, for instance, they are outside all the spectral line of the hydrogen atom as known when isolated from the rest of the universe. Here we are talking about different type of hydrogen atom. In the sun, we are talking about hydrogen atom compressed in an interior condition which are very, very heavy. So we expect some deviation from quantum prediction regarding the spectral line. So the study of this anomalous flame temperature is very interesting from a fundamental viewpoint. This is the certification of the flame temperature of magna gas you can find in the magnagas.com website. The next problem that I will recommend for research is a deeper study of the magnecular combustion, a new form of combustion that apparently is much more isoenergetic than conventional molecular combustion. You will hear a number of talks during this gathering, and so I would like to avoid entering into technical details. The next topic that definitely I would recommend for study is to go deeper into the structure of liquid water. Of course, the obvious statement is that there have been magnificent papers written in the liquid state of water in the 20th century. But in my view, they're not necessarily. They represent the final saying in the problem. The reason being because they are not quantitative. I do not see the equation producing an attraction between two or more water molecules. And so I recommend the quantitative studies that in our view, the liquid state of water is a magnecular state. Because here you see the hydrogen of a water molecule having a toroidal configuration, so therefore they have apparently an attraction. But independently from that, let's remember something very fundamental. Namely that water boils at 100 degrees centigrade. Water boils at 100 degrees centigrade. What does this mean? This means that at 100 degrees centigrade, the bond between water molecule is broken, and the liquid state is transformed into a gaseous state. This is known. But the question is the following. What is the force in nature that is broken by temperature? The answer is known. Magnetic forces. Magnetic forces, magnetic effect have a Curie temperature at which they disappear. They are disoriented and are no longer statistically valid. So therefore, it appears that 100 degrees centigrade is the Curie temperature of the magnecular bond characterizing the liquid state. If this is correct, then the application, the industrial application, are very significant. For instance, to the gasoline molecule that is still mostly unknown. Therefore, we can improve its combustion and decrease the pollutants in the exhaust. Finally, and I would like to close this lecture with this recommendation, and namely that we should perhaps study together this new class of fuel, of fossil fuel, that I propose under the name of high gasoline, HY diesel, HY coal, etc. Those are essentially new fuels because they are composed of hydrogen in a molecular form, which is chemically bonded by a molecular bond to ordinary fossil fuels such as hydrogen, diesel, and so on. But hydrogen has a very high flame temperature. So if we succeed in this bond, then the high gasoline, high diesel, they can be so pure that they may not need any catalytic converter at all, because the byproducts of combustions are combustible, such as hydrocarbon, CO, etc. They are combustible. If we have hydrogen bonded to the fossil fuel, those the contaminants should burn, increase energy output, and increase significantly, if not dramatically, the combustion, the contaminants in the exhaust. You should know that there is a possibility of forming a new public company listed in Wall Street that may be dedicated to the study of these new fuels, and I would love to have a participation from India. However, I have to be very, very clear on this, that this type of studies require large amount of funds. $1 million for fuel is the bonus of the chief engineer of British Petroleum at the end of the year. Now, of course, we don't need $100, $200 million to set the foundation, but nevertheless, there is the need of a number of millions of dollars even to get started. Otherwise, it's not worth it even to initiate. But if there are funds available from India, America, or Europe, and the contribution, the mind of the contribution from India, I would love to dedicate myself to the development of those new fuels. I would like to close this introductory lecture with a wish, and that future generation, maybe young generation present in this audience, may one day study the DNA via the use of hyperchemistry. This is far from being trivial, because this type of understanding will allow us all sorts of advancement, not only in diagnostic, but also advancement in cure, such as will automatically imply the use of hyperchemistry in biology, will certainly imply in due time and after due investment, will certainly imply new, better drugs for use to mankind. Again, thank you for your attention, and best wishes for this conference.